Hi, first of all, thank you very much for coming. Appreciate it. My name is Bill Porto. I work for Redpoint. I developed the machine learning software over there. And first of all, I want to tell you there's a card on your seat. If you need more information on this topic, there's a white paper. We'll send you that. That's basically all it is we don't want to take your information. Google may want to take your information, but we just want to send you the white paper if you're interested in the topic that we're talking about today. The other thing is that I don't have an outline. I think that's a waste of time myself. So again, just follow along. You'll be fine. Again, we'll get through this. See if this thing works. Okay. Because my company sent me out here and they're paying my way, I was told I get to advertise them just a little bit. So our company is based out in Boston. It's actually quite a bit like Dublin. It's cold, it's wet, and it's full of people with funny accents. So we have a lot of different software products and basically do customer relationship management, machine intelligence, and also some data management software as well. So we've got our fingers in a lot of different pies. Also, I would be remiss, if not fired, if I didn't tell you about some of the awards we won from the people who give out awards. So evidently they're happy with what we do, and that kind of makes us feel good as well. And the final thing here is that, again, I don't think any conference is replete without having to poke fun at least one of the sponsors. The point here is that Hadoop is a relatively new technology. When you think about it in all different databases and all the different types of data storage, data manipulation, data processing software, it's relatively new. It's changing fast. If you look at all the different products that are added to it, whether it's Yarn, MapReduce, MapReduce 2, Zookeeper, you name it, those are even newer products. The pace is changing more and more rapidly every day. We've got to keep that in mind. The other thing, too, is that machine learning can be a complement to all of this. And my viewpoint on this is to take machine learning from just the learning aspect into actual machine intelligence, where it does a little bit more than what we traditionally think about. So this is, again, I think one of the biggest problems where people get stuck in a rut thinking about what they did in the past, and they got to do the same thing over and over again. A lot of people who use modeling and other types of machine learning techniques do it the same way they did 20 years ago, do it the same way they did 50 years ago. And we have to change that paradigm. We've got too much data. It's coming in at too fast of a pace. We have streaming analytics need to be in place. And you just can't do this by taking your data in a big silo, taking it over to the IT department to clean it up, taking that data, putting it over to the data scientist to make a model for you, and then after that, then you actually put it in place. By the time you've done that, you may have wasted weeks. You've lost opportunity. And that's a big loss for any company in terms of profits and anything else they're doing. Okay, so there are some basic tenets that I want to get out first. Again, this is my viewpoint on machine learning, so take it with a grain of salt. Yours may be different. But I think basic machine learning comes down to prediction. You've got to figure out what's going to go and what's going to happen next, all right? And you have to base that on some things that you've learned in the past. This is the second thing that I think people often forget, is that you need to optimize. Optimize the process chain, optimize your models, optimize every part of the system in total content. The world's just too dynamic not to do that. It's not a static world anymore. You can't even consider it anywhere near static. And finally, this is a big key also, is to automate things, because people just don't scale well. You have a man in the loop. That takes time, that takes money, that takes expertise, and that's something that you don't often have these days. So that's something to think about as well. Okay, this is in my viewpoint, so take it with a grain of salt. I think there's a big distinction between learning and instruction. And instruction is basically you're taught something and you do things on a rote basis. You learn it over and over and over again. You freeze that, and then all of a sudden now you can add, you can divide, you can do the basics of whatever it is that's out in life. That's what I consider static learning. You're done. Actual learning is a dynamic process. It's something that's done adaptively, and you continue this over and over. An intelligent system, in my mind, you need several different components. Number one, you need a memory, some way to store the data, some way to store your past experience, what you've done. You need some sort of prediction mechanism to say, hey, this is what I learned. How can I apply this? You have to have some way to assess, I did well, I did not do well. How well did I do? So that's an important thing. And finally, this is probably the biggest thing that most people don't put in there, is a feedback loop, because you have to change whatever you're doing to adapt. There's just not a static world, and this is probably the big thing, is a feedback loop. And finally, the adaptation. This adaptation has to be constant. So if you're going to put in place one of these machine learning tools, you have to constantly adapt this. You can't just keep this in an environment and say, this is the same thing you did before. You're going to use this in your business process. So again, it's the same loop over and over again. Let's see if this little pointer has. You get some data, figure out what's going on in the data. You take an action. This is your behavior. This might be putting out another ad campaign. This might be putting out a different product, changing a product, doing something different. You figure out how well you did. You assess your performance in some sense. There are a lot of different ways to do this. It doesn't have to be metrics. It could be any sort of performance assessment. And then you adapt, you change whatever you did before, and see how well you do again. So this is a complete loop, and it continues over and over and over again. So don't lose sight of that in any modeling that you're doing. I take the viewpoint that regression, which is a lot of the people do in their data modeling, is different than what I consider prediction. Regression is taking a look at the past, and literally that. A lot of people do their models such that they try to fine-tune it to get exactly what happened in the past and learn from that. That's basically what they consider overtraining, and that's a killer. The real and the true process of a model is not to do we're going to get this thing exactly, but it's to capture the essential components of what a system and a process have in backend. There's always noise on a thing, so you can't really model in anything in perfection, and you shouldn't really try to model for perfection. Okay, so I'm going to try to base this talk on two different types of modeling. Okay, I'll talk about a little bit of different ways to do this, and again, the concept here is to figure out and to tell you that there is an automated way that you can actually come up with the best model for the different use cases that you have, and you can automate that process so you don't need a lot of expertise. The data scientists can use this tool to speed up what they're doing and make your lives happier. So in terms of the models, I break this down to taxonomy into two different types of modeling. One is for supervised learning. That's when you have data and you have some correlated outputs. I did this and I learned that from it. Okay, and again, any of that correlation can be one different, multiple outputs, or whatever it is. Unsupervised modeling is a slightly different thing, where you did something and you gather data, but you don't necessarily have correlated outputs with that. So maybe just, you gathered so much data and you want to figure out how they cluster together or how they segment it. So that's how I break that up. The other way that you can use unsupervised modeling is if you don't trust the outputs that you have, that particular data that you gathered. So again, let's break that up in two different things. All right, so the first thing, in terms of different types of models, this is one of the models that people have used in the past. This is actually a decision tree, and it's used by a lot of companies. Microsoft actually uses this quite a bit. If your computer ever dies, the first thing you do when you call up to there, they use a decision tree. They go down actually a piece of paper and they look down. First of all, okay, did you plug the thing in? Yes or no? Okay, after you plugged it in, do you have the blue screen of death or the black screen of death? Okay, after that, they ask you the next question. Is your credit card valid so that you can actually pay the bill for them to diagnose this further? Okay, same thing. They do have their uses. This is a very static concept. If the data is static, it's actually very good. It can be very, very useful. If the data is not static, it's very poor. There's also one other constraint, is that sometimes you need to have full explainability about what you're doing in your decision-making process. For example, in the United States, there's a concept called redlining, and this is where the financial institutions cannot deny you credit for your race, your gender, where you live, or anything else like that. Okay, there's certain restraints on that. So there has to be a case of explainability for that. So if you get a loan or don't get a loan, they have to be able to say, hey, this is why you didn't get it. It was because you didn't make enough money, you defaulted on some prior history that you had in buying a car or something else like that. So that's a very big thing as far as explainability. Linear models. How many people here have actually taken a class in statistics? Cool, I like it. Math, good. First thing you did in the class is the professor probably stood up there and said, let's assume the world is linear, all the errors are Gaussian, everything is equal. At that point, you probably should have raised your hand and say, hey, that's not reality. What's going on with this? Okay? And that's actually the big problem. So again, the math has been around for a long time. People use this. They still use this, and it's a commonly acceptable technique. And basically, you draw a straight line through a bunch of data. Well, it's easy to draw a straight line, and if you can't draw a straight line, you get a ruler to do that. But the problem with that is that real data is rarely linear. And what happens also is that you have errors on the top over here that are considered equal to the errors on the bottom. And that's really not valid. And again, all the different decision regions that you can get with linear or nonlinear thing. Okay, is that really a linear decision region? Is this nice and separable? This is certainly not. So that's not necessarily a good technique for that particular class of models. So you can adapt that a little bit. Okay, let's assume that you can have nonlinear models. All right, fine. So you make some similar assumptions on it. You say that the data is well conditioned, and all the errors on the plus side are equal to the errors on the minus side, et cetera. And then you assume sort of a fit. My curve is a polynomial, my curve is an exponential, it's a logistic, whatever. What's the best one? You do it by I. Do you do it by seat of the pants? You did it last time, the data fit. Well, that's really not a good way to do your data modeling. And you can have a lot of errors in what you get, and you get the right answer to the wrong problem. Here's another possibility for modeling. Some of these nonlinear models. How many people have heard about neural networks or artificial neural networks? Great. That's fantastic. They came around in the late 80s when they figured out how to train these. They've had pretty darn good success in a number of industries. I mean, they use them everything from rice cookers in Japan to running elevators. I mean, it's actually pretty good technology. There's a guy named Kolmogorov. He's a Russian in the late 50s, came up with a theorem that said these are universal modeling tools. You can actually model any particular function with this type of thing. That's good news. The bad news is that he didn't say how. He didn't say how these things were constructed, and that's really a difficult thing because there are a lot of different ways to do this. See these layers over here? Data comes in, it's processed through these layers of nonlinear functions, and they have all sorts of weights on them. They can be constructed in many different ways. The processing nodes can have many different functions. The challenge is to pick what are the right nodes, how to train the thing, how to construct them, how to put feedback loops. Maybe you have loops that go back one, maybe you have loops that go back to itself. That's still a black magic, somewhat of an unknown science. The other downside with this particular type of a modeling tool is that explainability kind of goes out the door. You almost have a black box approach. And that's something that people just, again, why they might turn to some of these other techniques. They're very, very powerful. And if you've ever heard about deep learning, this is basically what they're talking about is that, for example, in this particular diagram over here, instead of just one hidden layer of nodes, they're adding multiple hidden layers of nodes. And that's really good if you have a lot of processing power. So if you're IBM and you have Deep Blue or some other big processing machine, you can do that in the background. You can keep this thing running for days and days and days. Cool. If you need to do this fast to get a good turnaround for your product so you can learn something and get a model that's useful, not really all that applicable. Okay, so how do you use some of these things? Here's a typical thing. Maybe you want to predict whether the person is going to drop your product or be retained. So again, it's pretty much a flat type of information construct. So you might have customer ratings. You have information about retention, whether or not they're retained in the thing, and some other characteristics. Some of these may be text, some of these may be binary, some of them may be floating point, enumerated data. Computers are going to have to take that into numeric constructs because basically at some point that's all the computers do is binary bits, etc. Okay, here's the same processing chain. I think the talk this morning emphasized, and I can't emphasize it any more than that, is that you should really keep this in the same processing chain. You don't want to have to take your data outside of one particular processing chain, do your cleansing on it, do your sanitation on it, bring it over to another set of people who then ship it off to a set of people who have tables in it, then process it through the data science people, get the model, and then you actually use it. It takes too long. You just really can't do that. But the basic processing chain is the same. You get multiple sources in there. You select your input-output features. What do you want to call input? What do you want to call output? It can be multiple inputs, at least one. It can be multiple outputs, at least one. And then you transform them. Maybe you take out the enumerated values and make sure that they're in numbered form. And then you train the model. And it takes a little time, but you can definitely get through that. In terms of prediction, using the model afterwards, it's identical except for the training step. So all the same data comes in from different data sources, but it's the same type of data. And it's, again, apples to apples, oranges to oranges, but you can't really mix them. You can't say I train on this, and then I'm using it for something else. And the only thing you do is you freeze the weights, you freeze the particular model for that period of time. Once you get your decision, you can start training again. You can add another piece of data. You can have a sliding data window on that. Then you can act on the predictions. And this is the big thing here, is that once you get that model, you put new data through it, and you make an action happen based on what you did. Okay, so this is where the process can potentially go wrong. We recently had a customer came up to us and said, okay, we've got a lot of data, we want you to take a look at it, and we want you to predict whether the person coming into our store next is going to buy a sundry item, a coffee, a sandwich, or something else like that. And by the way, here are 500,000 rows of representative data for you to train on. Great. Took a look at this data, and I don't know if you can read back there, but one of the things that really pops out at me, virtually every single one of these data characteristics is 0. When I took a look at this initial analysis, I thought, okay, I must have had the wrong data set. So I asked for another million rows at this point. It's the same thing. I could count the number of non-zero things on each hand. That's not representative. So they asked for a model, and I actually trained them a model, and guess what? The model said, guess what? Predict 0. Not going to buy. They weren't too happy with that, but that's what the data said. So this is a good case where you're data rich, but information poor. And there's a big distinction between information and data. All right, so let's go on to clustering, where you don't have any sort of an output that's correlated with it. And you just want to figure out how the things are segmented together, how are things clustered. Well, collaborative filtering is one of the possibilities. This is basically used by many different companies out there. And it's basically a group type thing, where you have a bunch of people who've taken prior behaviors, and you come up with some sort of an assessment who's most similar to the people that you're trying to gain information from, and then you predict based on that. Okay? It's very easy to implement. It's very easy to modify. It's something you can modify in real time. It adds up. It's just basically summing a bunch of numbers. This is where it can go horribly wrong. Okay, I'm a mathematician. This is your one equation for the entire show. About 2 years ago, we got another puppy. All right? And anybody who's had a puppy, the first thing you remember is that they chew everything. They will destroy anything in your house. Doesn't matter whether it's furniture or the TV remote. They're highly destructive. Great little creatures, but, they're highly destructive. So I went to Amazon. Amazon, fine, let's get a baby gate. Let's get several baby gates. Cool, that worked. The following morning, I get all the advertisements from Amazon. Hey, would you like to buy baby formula? Would you like to buy toddler shoes? Would you like to buy all these different baby-related products? I don't have a baby. I bought dog calendars in the past. They didn't assess that in their makeup of me. No, they thought I had a baby. I can't turn this thing off. They're constantly doing this. I mean, if you know anybody at Amazon, let me know, because it gets worse. 2 years later, now, guess what? They have actually age progressed our little fur child. Okay? We're getting ads for toddler clothes, Fisher-Price toys, everything. Okay? So again, this is generalization technique. It's certainly not a personalization technique. So think about what kind of models you're going to throw into the mix. One of the keys here also is similarity metrics. How do you judge, anytime you need to cluster something, what is similar to and what is not similar to anything else? All right? And the typical scoring metrics, here's one that people use, just kind of add up how many things are common and how many things are not. And you get a complete wrong mismatch. Two women may be much more similar to a man and a woman, even though the similarity score that was chosen for this was what people commonly use. Okay, so then another assumption comes in anytime you do clustering is that how many clusters really are there? You might have marketing constraints that say we have 5 products, you've got to divide the world into 5 clusters. Okay, well, I mean, that might be acceptable, but in the most case, you don't know that. And it may be that 3 clusters are better than 7 clusters or 6 clusters. You really don't know that a priori. But there are ways to measure that. And if you have to take a model and redo it and redo it and redo it manually, it takes a lot of time, takes a lot of effort, and you may be missing something along the way. So again, this is where automation is going to come in. There you go. Another thing in terms of modeling is that if you're going to do clustering, what are the types of models that you can apply to this? Anybody heard k-means modeling, k-means clustering? Great. Okay, that's just one of many. That makes a big assumption that your data is nice and distributed and that you can actually draw these nice round circles around it. Okay? Well, that may be the case, but what about ellipses? Maybe that models the data better. Maybe that's a better technique for you to use. And if that is, why not use it? So if you're stuck using this, you've missed a lot of information that could gain you market share or some other type of an increase in your business sales just by the fact that you didn't choose or you didn't even look at other types of models. Here's another type of model. This is a self-organizing feature map. There's a guy out in Finland, Teuvo Kohonen, who came up with these in the 80s. This is a technique where you basically take high-dimensional data with many, many different rows, or many different columns, and you reduce it down to maybe 2 or 3 columns. So in this case, I've got 2 dimensions and a color dimension. all right? And so this is some data that's been trained, and you get essentially what are called heat maps, and you can then say, okay, well, maybe this is unemployment percentage versus average age, or different viewpoints on the data. The nice thing about this is that if you take a look at this like a topology or topography, you can actually figure out who's on the edges of this. And that's very important. People just neglect that crazy. They say, okay, well, this is in one cluster, I'm going to use it for this. This is in another cluster, I'm going to use that. But in reality, these guys may actually be the most important people for you to figure out, the people on the edge boundaries. Those are the swing voters in parlance, that you might be able to alter your product, alter your technique, alter your behaviors of your company to gain that person into what you want them to do, to buy a product or to move them into a different category or whatever you'd like to do. So again, this is a very powerful technique. People typically don't even think about that. So the thing is that there are many, many different techniques that you can use. It's the same type of process in terms of clustering as we did in the prediction. The only difference is that during the training, you don't have any truth data, or you just assume that it's not something that's correlated or you don't trust it. And then same thing with prediction. After you do your particular, same input processing chain, then you can go ahead and say the person was in cluster 1, cluster 2, cluster 3. It doesn't have to be binary. Most people do binary, but it doesn't really have to be binary. So this becomes the biggest problem. People just don't think about this, and they have to do this manually. So after choosing the model type, which is pretty easy, you either have truth or don't have truth, what do you do? How do you choose the model to use? How do you automate that process so that you don't have to think about that and spend a lot of time? What kind of parameters? Every one of those techniques we talked about has a number of different parameters on that. And those are things that you have to think about. Or do you? This is where I think the entire industry could use a little bit of help. It's actually optimization of the modeling process, optimization of virtually any process. There are a number of standard techniques people have done in terms of optimization. Gauss has come up with different optimization techniques, and Newton came up with and we're talking about 200 years ago in terms of some of the theory. Those typical techniques, again, when people try to apply them, they get the right answer to the wrong problem because either linearize it or they come up with the wrong type of function to assess how well things are doing. They say it's continuous. Well, the world's not really continuous. Sometimes it's discrete. They say it's differentiable. Well, that's force-fitting your particular function to fit their math, and that's not something that really will help you much. But you can use something that's been around for a while, simulated evolution. And evolution has been working for several billion years here on Earth, and it's done a pretty good job in terms of making us here. And we're fairly intelligent creatures. Well, most of us are, until you see some of the drivers out there. It's a very efficient search technique. The beauty of this particular technique versus some of the other standard techniques out there is that you always have a solution. And you can start with an existing solution. If you have a hint on something, you can actually seed the population of solutions with that. And then after that, you can have any sort of arbitrary evaluation function. I'm going to get to that in a second. But the basic things are here is that you have some way to vary your model. And again, say you have clustering technique. 1 cluster, 2 clusters, 3 clusters. Those are variables you can use. What kind of model? You're going to use a k-means, a k-medians, a feature map, ellipsoidal thing, a Gaussian mixture model. It makes no difference. Throw them into the pot. Those are things that you throw in, and then the technique actually says, okay, let's try this. Let's see how well this does. If it does well, let's keep it. If it doesn't, throw it out, vary it, try it again. Okay, so it's, again, the same cycle in terms of variation, assessment, and selection. This is probably the biggest thing in terms of business prospects, okay? Because this technique can use any sort of arbitrary measuring function, you can have these types of asymmetries. Say, for example, and again, Dublin is very similar to Boston. Luckily, I don't live in Boston, but if I did, I might be a little bit aware of this. So say if I had a fitness function that said, if I score sunshine correctly, I'm the weather broadcaster, I get 20 points. Cool, okay. If I said it was a hurricane and I guessed it was a hurricane and I broadcast over the news, I get 50 points because it's worth a little more. You're not going to go out in that. What happens if I predict sunshine and I get a hurricane? Disaster. That's the same thing in terms of business where you have maybe the cost of acquisition of a customer is completely different than the cost of losing a customer. So this type of asymmetry is something that's very well suited to this evolution construct. Here's an example that we used on an actual customer, and they asked us to predict whether or not their data would show a new customer and an existing customer as being someone who would drop their plan in an insurance industry or keep their plan. And they were using a typical modeling technique. I won't even say what it is, but it's one of the linear methods. They didn't even consider some of the other techniques that were out there. So we threw this into the same type of process chain and said, let's see what happens if you let, instead of the person, the human, pick the model that you think is the best, let the machine automatically come up with this and just evolve what it thinks is the best model for it. In reality, in terms of utility, you don't care what the model is. You just want the best model that's robust to the situation. And if it happens to be linear, great. If it happens to be nonlinear, great. If it happens to be this, it really doesn't make any difference because it's the utility of the model that really counts. It's something that you want to be able to use in a fast enough time to make it relevant so that you can make a decision and then pop new data through that. So this is a case where I actually started out, and again, I ran this particular example, and this is, again, where their particular model. And I think they came up with a performance score. I just normalized to 62% there. And just within 6 generations of this evolution process, we gained them 10 percentage points on this chart. That's huge for an industry. I didn't monetize it in terms of how many dollars. I'm sure that they could probably do that. But that's a huge gap. They would never have seen that as a possibility with using their current modeling techniques. And yet this is an automated modeling process that they basically had to press a button and said, go do it. That's about it. And that's a huge thing for them. They didn't have to employ extra data scientists. They didn't have to have extra IT people. The data is just there. They process through the same process data chain and let the algorithms, the optimization come up with, hey, this is better than that. Throw out the bad ones, keep the good ones. Do this over and over. In terms of a number of different solutions, different types of models that were picked, different types of parameters, this is about 100. I think this was I started this population with 5 different models. Each one varied about 3 different offspring models. And we just repeated the process through 6 generations. So 100 different models later, that's what we came up with. And that's a significant gain. So here's another possibility for use of the same technique, incorporating a data model in actual business processes. So this is where you might have historical data. You put it in your database. It doesn't matter exactly where it comes from. It's just the fact that it is data and it's stored somewhere and it's accessible. So you train and you update a model, okay? And then you also have some sort of operational trigger point. A lot of people are not comfortable with using these automatic techniques because they've been used to using something in the past that they just like to do. Okay, cool. If you don't have enough data, that's another reason why you may want to do this after you gain enough data to train a model that's statistically robust. So maybe in this case, you don't have enough to do it, so you say, I want to just use this A/B testing that they're normally doing. Great. Do that for a period of time. In the meantime, what you're doing is you're training a model, and you're doing that in the background process. Once you want to turn it on, you flip the switch. You say, instead of a manual mode, I want to change that into the automated machine learning mode. And at that point, you can take an action based on that instead. You can always take a look and throw the switch the other way, and maybe even want to throw this into a mixture of some amount of randomized, current method of doing that with some amount of machine learning. And then pick and choose to make whatever decisions that you want to. And you can do this on the fly. The big key here is this feedback cycle. Don't stop the process. So any new data, anything that you did, any stimulus that you presented to the customer or to your process chain, or maybe just changed in the manufacturing process as you did, for monitoring some sort of vehicle fault or any other process that you can think of, you made a change. Use that information to update your database as you would normally do, and retrain the model. You can do this with a sliding window. Maybe you only want last week's worth of history. Slide it every single day. Maybe it's just taking a single data point in and retraining with that, drop off an old one. Typically, you don't have room in your database and or memory to train in a reasonable amount of time just by keeping the world growing, so you have to limit it to some extent. But this is a very, very valid cycle, and this has been implemented many, many times very successfully. So again, something to think about out the box. So again, the takeaway on this one is keys for successful machine learning. Don't assume if you don't have to assume. Let the data speak for itself. Data is data. There's information in the data, but don't assume that the data has this distribution or that distribution just because you did it in the past, because you like it, because Gauss said it was. Well, guess what? That's not reality. So again, don't force fit your models into what you think is happening. Let the process decide what the best model is and use it. Trust it. I mean, this is new technology. It's not just for the marketing space. The DoD, American defense industry, has been using this for a long time. The biopharma industry has been using this for a long time as well. Another key, again, the cost of acquisition is not the same as the cost of a loss of a customer. All errors are not equal. So you can't really assume that some of these techniques with the least squares techniques are applicable to all of your data and data models. Okay? So don't force fit at that. Again, continual adaptation, don't stop the process. The moment you stop that, you stop learning. That's it, you're static. And you're going to lose market share. Because someone else is going to keep the modeling process going, keep the adaptation process going, and they're going to be ahead of you. So you've got to keep that going no matter what. If you can keep humans out of the loop as much as possible, you'll do this a lot faster. Again, a lot of people want to be able to have that hand on the red button saying, okay, halt, I don't trust it yet. When Tesla comes out with their first fully automatic driving car, all on the road, I'm sure people are probably going to be scared to death of these things, and they're going to want to have manual override. As far as I know, the tests that have actually come out originally last summer, I think, when they first started this, people are starting to trust that, just in the 9 months since that. Okay? The systems are actually working. So trust it. Optimization, this evolutionary process actually works. It works very well. Again, I mentioned the biopharma. The banking industry uses quite a bit. Automatic stock trading is done by the same optimization of process, what the portfolio should be, what the portfolio shouldn't be. The pharma industry, drug design. Again, this is proven technology. It's been proven in biological circumstances. Again, we're all here. We're a pretty good success rate for that. So trust it. It does work. So that's it for me. If you have any more questions, we'll get on that. And before we go any further, again, remember, fill out your card. There's a white paper. It's available for you. Just let us know if you want it, and we'll get it for you. So with that, I'll go for questions. Dead silence. I like it. Yes?
Where do you see the role of humans in your world?
One of the biggest roles is during the initial machine learning steps is the cleansing of data. Okay, you get a lot of garbage data, and we've seen it with just about every database that's been handed us by every single customer. It comes from different sources. The addresses are all in different formats. All the different fields have different names, even though they mean the same thing. You have to do joins, you have to do tables, filters, everything else like that. So that's definitely one step. That's data cleansing. Second step is that all of these techniques will do better if you don't throw everything into the pot at the same time. You can't just say, here's a neural network, I got 1,000 features, let's just throw it in and see what sticks and what doesn't. It just doesn't work. It takes too much time to do that. Theoretically, you could, but by the time you do that, we'll be long gone, or our grandchildren will probably be long gone. It's just not practical. So those are two aspects where I think you can do a human intervention. What I see as one of the biggest problems so far is to make the process easy for people to use. You know, the easy button. Because I see a lot of different users out there, and they're different types. Data scientists want to be able to drill down, get all the parameters. Let's twiddle this, etc. There may be some marketing people that just want an easy button. Say, press this thing. I want a model that's ready in 5 minutes, so I can deploy it immediately. Because the new product's coming out tomorrow, and I need to have some feedback on that and be able to adjust the parameters. So those are some of the key aspects. I'm not trying to take away jobs from other people. I'm trying to augment that mentality that we have to do fully manual modeling at this point. Next question. Sure.
What's for you the difference between statistics, machine learning, and analytics?
Okay, so the question is, what's the difference between statistics, machine learning, and analysis or analytics? Okay. Analytics traditionally is you took a look at a lot of plots, take a look at a graph, okay, maybe did a little regression testing on things, and you show it to your boss and say, this is what I think is going on. That's what happened. I think analytics is actually more than that, because it's a total data analysis of what the processes are. And I think you use machine learning to help you with that. Because if you put a process in place like an optimization on some sort of model, you're going to get a result. And then you have to analyze that result and say, hey, what was the lift on this? Did we get something that worked better? Did it work worse? Maybe it's in a website design. Maybe you want to say, okay, what are the different colors that make people respond better than other colors? That takes a little bit of actual analysis on it as well. And then the analysis also comes into the fact that, well, what are the options of things that you can do? Okay, maybe this, like I mentioned, with the explainability of that one particular type of model, that's a key. Because if you don't have that and your customer demands that, you're out of luck. There was a project I worked on for the FDA. And the Food and Drug Administration, actually, if you don't know about this, all the containers that come in the United States, they have to go through different ports. And they have, like in Los Angeles, they got a handful of inspectors. And they probably have thousands and thousands of these containers every day. Problem is, which ones do they analyze? Which ones do they look at? So we came up with an algorithm, we came up with a system for them, some models from predicting. Did great. They came back to us and said, we can't use that at all. Because the guys who have the containers, they want to know why you red flagged them. They want to say, hey, why did you pick me, not them? You know, you're picking on me. And no, so we had to come up with a different construct, again, the decision tree project. And that allowed them to say, yes, you were red flagged because your manifest said you should have come through Singapore and you actually came through Taipei and you're supposed to be here in 3 days and you actually came in 7 days and our GPS tracking shows you went to a couple other spots. Red flag, you were hit. In terms of statistics, the statistics are all underlying a lot of these things. Statistics come in terms of the evolutionary algorithms as well, because you can show that they actually will converge to a solution. Maybe not fast, but they will converge. So then again, those are important parts. But most people use statistics to prove what they want to prove or to do something, a process that they've done in the past over and over again and justify it. But statistics are just that. They're just numbers. So, that's my opinion. Yes? That's actually, okay, so the question is, how does the evolutionary algorithm handle the fact that different model types have different parameters? Okay, so each different type of model has a set of different parameters. And if you think about those as mutable types of things, so say if you have a regular k-means clustering model, what are the types of the things that you can vary with that model type? We can model with different cluster numbers, so you can say I want 2, 3, 4, 5, 7 clusters, pick a number, so that's a variable. The other thing people don't recognize is that the starting point for that particular model makes a difference in the outcome. So if you take a different starting point, and you randomly say, I want to start with this, and you run the k-means algorithm on it, you get a different answer than if you had a different starting point. So that's a point of variability for that model. So for each model type, you say, these are the things I can mutate or vary, and within that set, you randomly draw and say, okay, I'll roll the dice, okay, I'll vary this. How much you're going to vary? What's the range of parameters? So maybe the minimum number of clusters is obviously, well, I mean, you could have one cluster. Whoopie-doo, who cares? So probably 2 clusters is a minimum. And you might want to say a maximum cluster number is 20, because past that is unrecognizable. So that's one case for that. Maybe in the neural network, you might want to say how many nodes, how many layers, how many types of different functions it has. So those are variable parameters for that one. Each one of the different modeling types usually has something you can vary. The linear least squares models, maybe not so much on those, but you can still throw them into the pot. And maybe for that, you throw in and out different inputs. So you can pick and choose. Say, I'm going to use this set of inputs this time, see how well it did, and throw a different set of inputs. Maybe take out the first input and put the 7th, 8th, and 9th input in there in replacement, and then allow that as a variable parameter. So again, if you keep along with each model the types of things that they can do or types of things that they can be varied, then it's a very efficient process. Any other questions? Yes?
What is your preference about ensemble models?
From personal experience, I find, the question is what's preference on ensemble models? Personal experience, I find it helps robustness to a certain extent, but also averaging doesn't always gain you something. Just in terms of information content, anytime you average things together, you lose information. So again, maybe this goes back to your analysis question, is that to do the modeling with the ensemble method, do it without the ensemble method, and then have the analyst take a look at the results and see whether it makes sense to use the combined ensemble to generate whatever it is that you want in your final product. It's really not a clear-cut thing. It's kind of a shades of gray type of a question there. And I don't think there's really a clear-cut answer, and sometimes it's applicable, sometimes it's not. So. Yes?
How do you characterize AI versus machine learning?
Okay, so the question is, how do you characterize artificial intelligence with machine learning? Machine learning, typically, people talk about modeling, taking the model, do some prediction, and do something with it, and use that, whatever. I think artificial intelligence is actually greater than that. I think it's actually, I wouldn't even call it artificial intelligence so much as machine intelligence, okay? Where you can actually put systems in place and take that system and have it learn. And we were talking about this morning in the keynote address, they're talking about all these little different processors. Maybe the Raspberry Pi is gathering data, transmitting something else, et cetera, and then aggregating those. Each one of those little devices can learn something, and they can pass it on to another. They can pass that larger. They can aggregate, and they can segregate the information. I think that's where artificial intelligence really is going at this point. And I think it's the entire construct of prediction, optimization, and automation that really constitutes machine intelligence or artificial intelligence, if you want to call it that. So, again, if you have questions or whatever, I'll be outside. Please fill out the card. If you want more, there's white paper available. We'll send it to you. And, thank you very much for coming.